250-degree termination refers to the temperature rating of the terminal blocks or lugs used to connect the grounding conductor to the equipment enclosure. In the National Electrical Code, terminal blocks and lugs for grounding systems are typically required to be rated for a minimum of 250 degrees Celsius, which equals 482 degrees Fahrenheit. 7,000 amps of fault current represents the maximum fault current that the grounding system is required to handle. The National Electrical Code specifies the minimum size of the grounding conductor based on the maximum fault current in the system. The 1.56 multiplier is a constant used to convert circular mils to square inches. The formula is area in square inches equals circular mils divided by 1.56 times 10 to the power of 6. The National Electrical Code provides a table 250.66, that specifies the minimum allowable cross-sectional area of copper grounding conductors for different fault currents. These areas are given in circular mils. To convert amps to circular mils, firstly, find the maximum fault current in the system. Secondly, refer to table 250.66 and locate the row for the maximum fault current. Thirdly, note the minimum allowable cross-sectional area in circular mils. For example, if the maximum fault current is 7,000 amps, the minimum allowable cross-sectional area of the copper grounding conductor is 20 to 27 circular mils. The 250-degree termination and 7,000 amps fault current are based on worst-case scenarios and provide a margin of safety. The 1.56 multiplier is a mathematical constant that converts circular mils to square inches. The relationship between amps and circular mils is based on the conductivity of the conductor material, copper in this case, and the desired current carrying capacity. When dealing with electrical systems, grounding is a critical safety measure. It provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices, such as circuit breakers or fuses, to quickly trip and clear the fault. This minimizes the risk of electrical shock, fire, and equipment damage. The National Electrical Code, or NEC, sets the standards for safe electrical installations. Article 250 within the NEC covers grounding and bonding requirements. Understanding the NEC is essential for anyone working with electrical systems, from electricians and engineers to homeowners doing minor repairs. The NEC specifies that grounding conductors must be sized appropriately to handle the maximum fault current that could occur in a system. Table 250.66 is a key resource for determining the minimum size of grounding conductors. This table provides the minimum circular mil area for copper grounding conductors based on the size of the ungrounded conductors. The circular mil is a unit of area commonly used in the electrical industry to express the cross-sectional area of wires and cables. 1 circular mil is the area of a circle with a diameter of 1 mil or 1,000th of an inch. To use table 250.66, you first need to determine the size of the ungrounded conductors in the circuit. These are the conductors that carry the normal operating current. Once you know the size of the ungrounded conductors, you can look up the corresponding minimum size of the grounding conductor in table 250.66. The table typically lists the minimum grounding conductor size in circular mils. It's important to note that table 250.66 provides the minimum allowable size for grounding conductors. In some cases, it may be necessary to increase the size of the grounding conductor to meet specific installation requirements or to provide additional safety margin. For example, if the grounding conductor is run a long distance, it may be necessary to increase its size to reduce voltage drop. The NEC also requires that grounding conductors be properly terminated to ensure a reliable connection. Grounding terminals and lugs must be listed for the purpose and suitable for the type of conductor being used. They must also be installed in accordance with the manufacturer's instructions. The 250 Celsius termination rating is an important consideration when selecting grounding terminals and lugs. This rating indicates the maximum temperature that the terminal or lug can withstand without degrading its performance. Grounding terminals and lugs used in high fault current applications must be rated for at least 250 Celsius to ensure that they can withstand the heat generated by the fault current. The 7000 amp fault current value is just an example of a potential fault current level. The actual fault current in a system will depend on several factors, including the voltage of the system, the impedance of the source, and the length and size of the conductors. A qualified electrical engineer should perform a fault current study to determine the maximum fault current that could occur in a specific system. The 1.56 multiplier is used to convert circular mils to square inches. This conversion is sometimes necessary when calculating the ampacity or current carrying capacity of a conductor. The ampacity of a conductor is the maximum amount of current that it can safely carry without overheating. The ampacity of a conductor depends on its size, material, insulation, and installation conditions. The NEC provides tables that list the ampacity of various types of conductors. These tables typically give the ampacity in amps per square inch. To convert circular mils to square inches, you divide the circular mil area by 1.56 times 10 to the power of 6. For example, a conductor with a cross-sectional area of 2227 circular mils has an area of 0.143 square inches. 2227 divided by 1.56 times 10 to the power of 6 equals 0.143. The relationship between amps and circular mils is based on Ohm's law, which states that the current flowing through a conductor is directly proportional to the voltage applied to it and inversely proportional to its resistance. The resistance of a conductor depends on its material, length, and cross-sectional area. Copper is a highly conductive material, which means that it has a low resistance. This makes it a popular choice for electrical conductors. The larger the cross-sectional area of a conductor, the lower its resistance. This means that a larger conductor can carry more current without overheating. In summary, grounding is an essential safety measure that protects people and equipment from electrical hazards. The NEC provides detailed requirements for grounding and bonding, including the sizing of grounding conductors. Table 250.66 is a key resource for determining the minimum size of grounding conductors based on the size of the ungrounded conductors. Grounding terminals and lugs must be listed for the purpose and suitable for the type of conductor being used, and they must be rated for at least 250 degrees Celsius in high fault current applications. The 1.56 multiplier is used to convert circular mils to square inches, which is necessary for calculating the ampacity of a conductor. Understanding these concepts is essential for anyone working with electrical systems. Always consult the NEC and other applicable standards to ensure that electrical installations are safe and compliant. Additional considerations when sizing grounding conductors include the length of the conductor, the type of insulation, and the ambient temperature. Long grounding conductors may require upsizing to compensate for voltage drop. Conductors with lower temperature ratings may also require upsizing to prevent overheating. The ambient temperature can also affect the ampacity of a conductor. Conductors installed in high ambient temperatures may need to be deaerated to prevent overheating. Proper grounding and bonding are critical for ensuring the safety and reliability of electrical systems. By following the requirements of the NEC and other applicable standards, you can minimize the risk of electrical shock, fire, and equipment damage. Remember to always consult with a qualified electrical professional for any electrical work. Working with electricity can be dangerous, and it's important to have the knowledge and experience to do it safely. In addition to the points already covered, it's worth noting the importance of equipment grounding conductors, or EGs. These conductors provide a low impedance path for fault current from the non-current carrying metal parts of equipment back to the source. EGC are essential for ensuring that overcurrent protection devices will trip quickly in the event of a fault. The NEC specifies the requirements for EGC in Article 250. In many cases, the metal conduit or raceway that encloses the circuit conductors can serve as the EGC. However, in some situations, a separate EGC must be installed. For example, a separate EGC is required when the circuit conductors are installed in non-metallic conduit or raceway. The size of the EGC is typically determined based on the size of the circuit conductors, as specified in Table 250.122 of the NEC. It's also important to ensure that all metal parts of equipment that are likely to become energized are properly bonded together. Bonding creates a low impedance path for fault current, which helps to ensure that overcurrent protection devices will trip quickly in the event of a fault. The NEC specifies the requirements for bonding in Article 250. Proper grounding and bonding are essential for creating a safe and reliable electrical system. By following the requirements of the NEC and other applicable standards, you can minimize the risk of electrical hazards and ensure that the system will operate safely and effectively. Always consult with a qualified electrical professional for any electrical work to ensure that it is done safely and in compliance with all applicable codes and regulations. Furthermore, it's crucial to understand the difference between grounding and bonding. Grounding connects the electrical system to the earth, providing a reference point for voltage and a path for fault current. Bonding, on the other hand, connects metal parts of the electrical system together to create a low impedance path for fault current. Both grounding and bonding are essential for electrical safety. A common misconception is that grounding alone will protect against electrical shock. However, grounding only provides a path for fault current to return to the source so that overcurrent protection devices can trip. Bonding is necessary to ensure that all metal parts of the electrical system are at the same potential, which minimizes the risk of electrical shock. When working with electrical systems, it's important to use proper test equipment to verify that grounding and bonding are installed correctly. A ground impedance tester can be used to measure the impedance of the grounding path. A low impedance is essential for ensuring that fault current can flow quickly and safely back to the source. A continuity tester can be used to verify that all metal parts of the electrical system are properly bonded together. The tester should indicate a low resistance between all bonded parts. Regular inspections and maintenance of electrical systems are also important for ensuring that grounding and bonding remain effective over time. Grounding and bonding connections can corrode or loosen over time, which can increase the impedance of the grounding path. Regular inspections can help to identify and correct these problems before they become a safety hazard. In conclusion, grounding and bonding are essential components of a safe and reliable electrical system. Understanding the principles of grounding and bonding, as well as the requirements of the NEC, is crucial for anyone working with electricity. Always consult with a qualified electrical professional for any electrical work to ensure that it is done safely and in compliance with all applicable codes and regulations.